Hello, welcome to the class on pressure. I am Laura Lewis. Just put full screen so you can all see it. Okay, so today's class is about pressure, and we'll be talking about how to work it out and so on. So let's look at our learning aims first of all. So we're going to look at an explanation of what pressure is and how it is calculated. Number 2, how pressure calculations are applied to situations in the real world, and examples of calculations involving pressure. Okay, so let's get started. Okay, so let's start with the definition. Okay, of pressure on a surface. So the pressure on a surface is the force measured in newtons divided by area. Okay, force divided by area. So let's have a think about some things that have to do with pressure. So at the top here, top 2 images, this shows a polar bear's paw. This shows a camel's foot. So they both have large feet compared to their body, so it looks a bit like different to a horse or something. It's bigger than the normal sized bear's paws. So the weight of the animals is spread over a larger area. Okay, so if you look back at this, so it's force divided by area. So the bigger the area, the less the pressure. Okay, so if you think about where these animals live, you've got the polar bear living on the ice, okay, and you've got the camel living on sand. Is that it's an advantage for both of these animals to have low pressure on the surfaces they stand on, because they could sink. Because the polar bear could sink into the ice, or break the ice, because they have to sort of stand on the ice and there's water underneath that, and the camel has to walk over the sand. It doesn't sink in the sand, does it? Okay, so yeah, it's got a large area. There's 2 other examples. We've got a different situation. So you've got, if you look at these sort of hills, they've got very, very small points. So they've got a small area. Okay, so there's not much of a bit here as well. So a very small area for the person's weight to sort of bear down on the ground. Okay, so they're called stiletto hills. This is kind of what they're called. So a very small hill area, and so therefore this area is small, the pressure is going to be big. So it's a force. So the force is the person's weight. So it's force divided by area. If this is small, the pressure is going to be very high. Have you ever seen anyone walk onto grass like that? You then probably will sink into it, into the grass. Okay, so or any sort of mud or anything surface like that. Not good to walk on grass with. Another example is you're hammering a nail into a piece of wood. So you can see the nail's got a sort of pointed point, and also the hammer's got quite a small area. That's why you'll sort of see sort of comedy things where people kind of hit their own thumb with the hammer. It's got quite a small point, okay, but obviously enough to hit the nail in. Okay, so yeah, exactly. So if you put a force onto a small area, that becomes a large pressure. So the pressure in that case is wanted. Obviously, it drives the nail into the wood. So yeah, you just it's small area. That's why you've got a small sort of bit here. Well, so if the nail with a bigger head, it wouldn't be as much pressure. It'd be easy to hit it, but it wouldn't be as much pressure. So you have to have kind of a medium there, okay, between the 2, kind of the best of both worlds. Okay, so that's pressure. It's force divided by area. Okay. So you know the type of pressure, other than the pressure just exerting things on solids, you get gas pressure. Is a very, very common one. So yeah, gas pressure is caused by collisions between the particles in the gas. So the gas is made up of gas particles and the surface of the container. So as the particles collide with the surface of the container, they exert a force. So it's actually the particles that are hitting the sides of the container and causing a force, which is felt as pressure. So we've got 2 balloons. One's not been blown up, like one you buy from a shop, as they are, and one that someone's blown up. So why do they get bigger? So you're actually filling it with air particles from your own breath, or pump you could use. And the more air particles you add, the bigger the balloon. Okay, so there's actually a pressure inside the balloon caused by the air particles hitting the inside. It's so small you don't sort of feel it directly hitting, but everyone knows if you get a pin and you put it into a balloon, it bursts. It's under a lot of pressure. All the little particles are bumping into the surface all the time. Okay. So another interesting thing, okay, is that if you put a balloon in the freezer, you can do this. It's a perfectly safe experiment. okay, it will decrease in size. If it goes in a very cold room, I did this one. I bought a birthday balloon once, with my family, and it was cold. It was cold time of year, and he went to a cold room in a conservatory, and yeah, it did. It deflated like that. It's quite an interesting science experiment. It doesn't matter what gas is in the balloon, but if you put the balloon in a cold air or freezer, okay, it will decrease in size. Okay, it'll actually go down like that. Okay, so the explanation sort of here is that temperature is actually the speed of the particle. So the hotter an object is, the faster the particles are moving, and so the faster it is, particles are moving, the more force they're going to hit the walls of the container with. Okay, and the greater the amount of pressure on the inside. So if you cool down the particles inside the balloons, let's go back one. If you cool down these particles, they'll actually move less. They won't stop moving, but they'll move more slowly, and they'll move with it'll hit the sides with less pressure. They're still moving though. So it's actually that reason. So if you heated up the balloon, it would probably burst. And it's that reason that you don't put aerosol cans, like deodorant cans, any sort of spray cans, near anything hot, like on top of a mantelpiece of fire or anything like that, because the gas inside is under a lot of pressure, like the balloon. And if you heat up the particles, it can blow up. Okay, so it's actually extremely dangerous. I'm always very careful of that, about anything that's got compressed gas in it. You have to be very careful and don't put in it anything hot. Okay, or moving the window in a hot day, trying to keep it away from anything like that. So yeah, so obviously it's actually very the theory of this is actually very helpful in terms of danger and things. Okay, so going into a bit more detail about this. Okay, so this man called Jacques Charles. Okay, French. So he set up a container of gas at room temperature with a movable plunger on top. The plunger, this thing can move up and down. Okay, so there's gases and it's being heated, and this thing can go up and down. So it's like that's the same thing, different positions. So he then heated the gas. So let's see what happened. So that's the original temperature one. So that's room temperature, probably about 20 degrees, something like that, depending on the time of year. Okay, heated it up and the gas expanded. Okay, so explain the results in terms of temperature, movement, kinetic energy. So you need to recap on energy as a video on energy. Okay, and types of energy. So kinetic energy is moving energy of the particles, the force exerted on the plunger, the pressure and the volume of the container. Okay, so think about that. So as he heated the particles up, the particles increased their speed and increased their kinetic energy, so they could hit the walls of the container with a greater force. And this force would cause the gas to expand, so they were hitting each other, cause gas to expand, okay, as the particles hit the plunger with a force to drive upwards. So if this wasn't movable, that if you kept heating it, the gas would try and expand, and yeah, this could like blow out walls of the container. But it was movable, so it allowed the gas to expand. Because yeah, when it's heated, the kinetic energy increases and the gas expands. Okay, ideas. So volume and compression. Okay, so just okay, so 3 diagrams. So what do you notice about the volume, the motion of the piston, and the force of the particles, the volume of the air, the pressure in the containers. So if you move, so this is just showing you that you can move the piston up and down. Okay, so initially if you put air and you move piston down, what would actually happen here? The volume would decrease and the actual temperature would increase there. So let's just get up full screen again. Sorry, a bit fast. So let's go over that a bit more detail. So when a gas is expanded, the motion of the pistons upwards. So if you expanded the gas like by heating in the previous video, so previous slide, the force of the particles is in the opposite direction. When a gas is compressed, the motion of the piston is downwards. The force of the particles in the opposite direction, because the particles will try and oppose your motion. Okay, here if you've got a bicycle pump, you probably know that if you try and sort of pump it, okay, and try and force the air out, you feel it sort of pressing against you. When the gas is expanded, the pressure of the container decreases. When a gas is, sorry, I'm just going to move that picture. I changed the format of the slide, and it kind of cut that word off. So let's read it again. When a gas is expanded, the pressure of the container decreases. When a gas is compressed, the pressure of the container increases. And yeah, if you're pushing it down, the air pressure here increases. Okay, yeah, you can find if you have a pump, bicycle pump, you probably can feel that. If you allow it to expand by heating it from the bottom or just pushing the plunger up, that the pressure decreases. Okay, 50%. This one slide. So you should think about using particles. So volume 1, volume 2. So you've got gas pressure and gas molecules. This is a good diagram to show you what's really happening here. If you've got more volume, the particles are more spread out and they're hitting the walls of the container. If you put the plunger down, you've got a smaller space and there's more collisions per surface area. Okay, so think about the surface area from earlier, link it in. If you've got a smaller space, there's more collisions per surface area and the pressure increases. This is why it's good to, it's about particles. Okay, here. So, so if you can write this out. Okay, so container 2 has a greater pressure as there is less space for particles to move. Therefore, each particle has a shorter distance to move before colliding with the surface of the container. Therefore, the increased rate of collisions between the particles and the surface of the container leads to a greater force exerted on the container by the particles. Yeah, this is a very key word here, increased rate of collisions. Yeah, okay, because they've got less volume, they've got less room, and there's increased rate of collisions leading to a greater force exerted. So this is very highlighted words are very important, okay, in terms of gas pressure. Okay, so we're going to look at some examples in more of a real world. I kind of discussed it a little bit, but it's always very interesting thing to do pressure is the way that it affects our weather. Okay, so lots of weather is to do with temperature and pressure. Okay, so you may have seen one of these in your own house. You may have seen it in a relative's house, your grandparents' house. I've got quite a fancy one actually. It's a barometer. Okay, it's a very good one, but it's quite a fancy one. It sort of sits on the tabletop. But these are all the things we call barometers, and they measure air pressure. Okay, like we were talking about, they actually measure air pressure. And when you see a chart like this on the weather, on the internet, on television, that these things here, these lines called with numbers, they're called isobars, and they join lines of equal air pressure. Okay, so different air pressure they join. So that's measuring pressure, and that's so according to the pressure means what weather you're going to get. And we're going to discuss that. Okay, if you want just a bit of a bonus information, these blue sort of looks like flags, is like bunting. These are called cold fronts. These red bunting is called a warm front. Okay, it's because it's that warm air sort of behind there, and that's cold air. And these things are called occluded fronts, where warm and cold air are meeting. Okay, but we're going to look at the atmospheric pressures for a minute, because there's a lot you can do with just the atmospheric pressure. Okay, so you might see in here it says fair, change, stormy, very dry. Okay, so there's all these different things. What do we know this? Okay, so we need to go back a bit. We'll look at the Earth's atmosphere and think about in terms of air pressure. Okay, so lots of people don't really kind of grasp the size of the atmosphere compared to actually the Earth. It's actually very thin, the atmosphere, compared to the size of the Earth. Okay, most of our atmosphere is actually within 10 kilometers of the surface. So we're going to compare it to the size of the actual Earth. So the Earth's radius, radius, that's a thing for maths. Radius is 6,400 kilometers. And the atmosphere, most of it, say even more of it's down here, but most of it's the stratosphere, you may have heard of, 50 kilometers. Okay, so it's actually very thin compared to the rest of the Earth. Even the crust, which is the bit that we stand on, is actually very thin compared to the inner Earth. Okay, so this is actually representing all the continents, things like that. That's actually very thin. The atmosphere makes up a very tiny part of this, just a layer of gas, okay, above the Earth. Most of it's nitrogen. Got some oxygen, obviously, to breathe, and the carbon dioxide only makes up 0.04%. Okay, you know, hear about it a lot. All of our weather takes place in something called the troposphere down here. Okay, and there's a you may have had the stratosphere and its ozone layer, because yeah, it's important. Some people notice it quite a lot. And by the time you've got the atmosphere, it's very, very thin, and by the time up here, you haven't really got the atmosphere anymore. Okay, so yeah, the atmosphere is a layer of air, sort of gases surrounding the Earth. Talking about gas pressure. We already know that pressure is caused by particles colliding with the surface. Yep, we already know that. So atmospheric pressure is caused by air particles colliding with surfaces. Yeah. Okay, so atmospheric pressure is approximately 100 kilopascals at sea level. Okay, I'm going to talk about a little bit more later about what that means. Okay. So why is it difficult to breathe at altitude? So if you go up the top of a mountain like Mount Everest, it's actually very difficult for you to breathe. So it's actually quite a simple explanation for that. So yeah, the force of gravity pulls the majority of air particles towards the Earth's surface. So this makes the density of the particles at low altitude quite high. So the air is quite dense down here. Okay. And the higher you go up, the less air molecules you have and less oxygen you have to breathe. So it becomes very difficult to breathe high up in Mount Everest. A lot of people have to have breathing equipment, or some people sort of train to actually live at high altitudes. Okay. So yeah, the density of the particles is actually quite low. Okay. So at high altitudes, why would the atmospheric pressure be low? Because the atmospheric pressure goes actually down, so it's actually very low atmospheric pressure at the top of mountains as well. Because there's just less particles to collide with surfaces, collide with you, collide with the ground, each other. Okay, there's less air pressure up there. Okay, so actually, if you fly an aeroplane, that should be adjusted according to how high you fly. It's actually important. Okay, so let's think about in terms of the weather, what this causes. So what I'm just showing you here is the winds on Earth, like the main winds. You have to sort of learn all this for science, but it's a very interesting diagram to look at. You get areas of low and high pressure. So high pressure is where the air is sinking, okay, causing a lot of collisions and a lot of air pressure on the surface. And a low is where the air is rising and there's less pressure on the surface. Let's think about, this is what I'm saying. So the molecules contribute to the pressure at this altitude. So surface air pressure is weight of air in column above unit area. Okay, so we'll talk about it a bit more. Okay, let's what types of weather do this cause? So high pressure, the air's sinking. So the air's sinking and putting a lot of pressure on the surface. So that actually means clouds can't form. Okay, because clouds are formed mostly by air rising and water condensing to form clouds. Like you see on a hot sunny day in the summer, here you see little fluffy, it's called cumulus, like cotton wool clouds developing. So the air is rising and it rises quicker on a hot day and condensing to form clouds. So when the air is mainly sinking, it's not rising, so a lot of time it's sunny. It doesn't always mean hot weather, so because in the winter time, that it can actually be cold and sunny. So cold and sunny, usually with a frost, usually because it's so cold. Fog can form there because fog is just a cloud that forms close to the ground and can't rise. So high pressure, fog, sunny weather, can be cold or hot depending on the time of year. Low pressure, so air is rising and that leads to the formation of clouds. Okay, when clouds form, that means we can get rain. So when we see low pressure on the weather forecast, that means often clouds and rain. Snow in winter. It's one of my favourite weather conditions, snow. It means snow in winter or rain in other times of the year. If we see high pressure, that means you mean sunny skies. Yeah, and it can be cold or hot depending on the time of year. Okay, so then that's why you can see in here. So you probably got a nice sunny day. Here, depending on the time of year, but it's going to be sunny. Not going to be any clouds or showers. Okay, then you've got low pressure area here. This is L for low, and over here low. There'll be lots of rain. So it'll be raining here or snowing here. Okay, depending on the temperature. Okay, so you're going to calculate, just to do a few calculations. Okay, so you could have what we showed earlier with pressure is force divided by area. Or we can have force equals pressure divided times area, because some people like to have a formula triangle. Okay, so you can do it like that. See, I would learn it as force pressure divided by area is the first thing to write down, but whatever you find easiest. Okay, I'm going to do some practice. I'm going to go out so I can write in. So calculate the pressure exerted by a person pushing a door with a force of 50 newtons and a hand area of 0.25 meters squared. So I think I've got a superscript on here, yeah. So I said let's have definition. Keep turning the superscript on. Turn it off. Okay, so force equals pressure divided by area. Okay, so sorry, it's I'll do it the other way around. Sorry, no? Just keep turning this off. So pressure equals force divided by area, because otherwise, yeah, if I do it the way around, we have to rearrange, and we don't need to rearrange. If we already know it, I was going to rearrange it for you, but we don't need to. So pressure equals force divided by area. So let's put numbers in. So pressure is force, is 50 newtons. Divided by area, 0.25 meters squared. Okay, so copy that. Okay, and that equals, so we've got a calculator out. 50 divided by 0.25, 200. So it's, and that superscript is on. The 200, right, so you probably think it's newtons per meter, which would be not wrong. It's a special unit called a Pascal. So it's 200 PA. Okay, I've got an equals out the same thing. Okay, so a little bit of a different one. The atmospheric pressure is on average 101, to be more exact here, 101,000 newtons per meter squared. What force is on a garden table of 4 meters squared? Okay, so here we're using one before. So if we look, force equals pressure times area. Okay, so we put numbers in. Easy enough. It's a big number, but it's a easy calculation. Okay, newtons. Yeah, 101,000 newtons per meter squared is equivalent to 101 kilopascals. Okay, times by, oh, that superscript is still on, isn't it? I had to write that squared and take it off. Times by 4. Okay, so we've got, we do our heads can't be 404,000 pascals. So it's straight away here, pascal, that's newtons per meter squared. Okay, and then calculate the pressure exerted by a hammer hitting a nail with a force of 500 newtons and an area of 0.007 meters squared. So again, pressure equals force divided by area. So force 500, got a big force this time, someone's hitting it. Area is 0.007. Yeah, always make sure you copy it down correctly in your exams or anything. Sometimes you can put some notes, it'd be quite easy to make a mistake. Cool. So, and we've always, in physics, we've always got a calculator. Don't worry about anything in your head. Okay, 500 divided by 0.007. Okay, it's very, it's quite a large number. Let's round it. So it's 71,428. That's 0.5. I'm going to round up to the nearest number, whole number. So 71429 we'll round up to. So 71429. Pascal. It's going into that little superscript. We don't want that. Okay. Okay, so very, high pressure, because we were talking about earlier about that nail. Okay, with the high pressure. So you can see here, the smaller the area, the higher the pressure. Okay, so thank you for joining the class. If you've learned something, you can always pause it and go back to it. Thank you for joining today. Hope to see you in a different session. Thank you. Bye-bye.